we have to compute the posterior probability. Okay, given the sample X, we have to compute the probability of the kth class. Okay, it can be class 1, class 2, class 3, and so on, or binary classification is class 1 or class 0. And the subsequent decision stage is the decision stage, basically where we use this posterior probability to take a decision. And we'll see that there are generally two approaches to solve the decision-making problem. The first one is this generative model. The second one is this distributed model. In case of the generative model, we'll see that we'll explicitly try to find or try to estimate the joint probability distribution. That means, let's say, probability of X and class, or maybe we can simply compute the likelihood, that is X is X given class, along with basically the prior probabilities. These two together will give us the joint probability, right? So that means we estimate the joint probability, and then from here, once we have computed this, from here we basically will try to compute the probability of the class given X, that means posterior probability. In case of discriminative models, we'll see that we'll directly try to compute the probability term, that means the posterior probability term, that is probability of class given X. In case of neural network, we have seen that we directly compute this, this particular posterior probability, right? And then we have seen an alternative approach where we simply take the input X and we come up with the decisions. Okay, those kind of functions or those approaches basically known as the discriminant function. Okay, we'll talk about more about them in the next lectures. Okay, so as we have said, in case of discriminant model, the inference problem starts with basically computing or determining the class conditional probability. That means the likelihood probability. That's, as you can see from here, this is the likelihood probability. And if we combine them together with the prior probabilities, so using the Bayes theorem, what we can have, we can easily compute the posterior probability. So that means basically our main attention is to find this joint probability or the likelihood probability. Okay, and these approaches are known as generative approaches because since we can compute this likelihood or the joint probability distribution, we can basically compute more and more synthetic data, okay, from the likelihood probability values. Okay, so that's why these models are known as generative models. In contrast, before going to this, this discriminative model, here I just listed some algorithms which falls under the domain of generative models. And in this lecture, we'll be basically talking about this naive Bayes classifier. Okay, just a list of names that I have given for you guys. Okay, another popular method you will see is basically the Gaussian mixture model, or in short, it is known as GMM. Hidden Markov model, that is, let's say, HMM. Okay, so normally you see that in time sequence data, often we'll use this hidden Markov model. Okay? But anyway, those are some advanced algorithms. So here we'll be simply learning about this one of the Bayesian network, that is the Bayes classifier. So in case of this discriminative model, so what we will do, as you can see from here, we try to determine the posterior probability. Okay, there is no intermediate step of finding the likelihood or the joint probability distribution. Okay, and this posterior probability will be used for discriminating. Okay, that's why these are known as discriminative models. Okay, and I have listed below the example algorithms which falls into the domain of discriminative model. And here we have already learned about this neural network. In the upcoming lectures, we'll also learn about this support vector machine. Okay? It means that basically what we do, we simply compute this posterior probability, because we have seen that in case of neural network, let's say in the output layer, so the last layer that we have is the output layer. And in this output layer, let's say if we are doing binary classification, so whenever we are using this binary classification, this node basically gives us what? The predicted outcome. And in order to get the predicted outcome, what we have seen that we have used this logistic, regression function, or logistic function, sigmoid of, let's say, z. Okay, so that means whatever the input we have in this node z, if we apply this sigmoid function, we know that if we see this function like this, the sigmoid function becomes something like that. So the values of z is from, let's say, minus infinity to plus infinity. It goes from plus minus infinity. Okay, let me try to work here. And then all the values are mapped in the range of 0 to 1. Okay, so this gives us the probability of falling into the domain of, let me write like this. It falls like this. So y equals to 1 given x, right? That means this y means, in this case, we can say this is our class 1. The positive class, the probability of being in the positive class given the sample x. Okay. I believe, do you have any questions here? You're listening to me, right?
Yes, sir.
Yes, sir.
Okay. Then the discriminant function, we have already learned about this discriminant function, where what we have done. Okay, so we simply compute a function, like in case of this generalized linear discriminant function, let's say where we have computed, let's say g of x is equal to w1 x1 plus w2 x2 plus w0. Okay, so once we compute this, the responses are either plus 0 or minus. That means, let's say if we take this feature space, that is x belongs to a 2D feature space, so we have the decision boundary, which is basically it's a line, right? It's a line. So now you say, let's say if this side is the positive side and this side is the negative side, so we know that this response g of x, this discriminant function will give a response of 0 if it is exactly on the line. If it's on the positive side of the line, then for these samples it will give positive responses, and if it's the negative side of the line, for these samples it will give negative responses. So have we computed any sort of probabilistic values here? Yes or no? Did we compute any sort of probabilistic value for this discriminant function?
No, sir.
No, sir.
No, we haven't, right? So but the thing is that whenever you give a value of x over here, automatically from the sign of this function, okay, so what we write it is from the sign of this function, we know that whether it should belong to the positive class or it should belong to the negative class. So this is, we can directly take the decision. Okay? That means the probability has nothing to do over here. So this is why this is known as the discriminant function. But we know that the discriminant function, we can convert it to a discriminant model. How do we do that? Can someone tell me?
Using a sigmoid activation.
Exactly. Use a sigmoid function or softmax function, we can convert a discriminant function into a discriminative model. Okay. I'm going to talk about a different kind of model. This is known as the graphical model, which is also known as the Bayesian network or belief network or probabilistic network. So what we do, we try to represent the dependencies with the help of nodes and arcs. Okay, because normally in a graph, what do you see? In a graph, we see that there are nodes, right, and there are edges, right. So what is represented by the node? We see the random variables. Okay, the variables that we have. Okay, those are basically represented with the nodes. Okay, let's say this is x, maybe this is y, and this graphical model is basically, the basic form is basically it's a directed acyclic graph. Okay, that means you don't have any edges, like you don't have any cycles. Okay, but the graph is going to be directed like this one. Okay, and if you have an arc, that means an edge from one node to another, it means that this random variable is basically dependent on this particular random variable. Okay, and you will see that for each of the nodes, you will have a corresponding probability values associated with this one. For example, here we can say, okay, what's the probability of y given x? Okay, this is what we can represent. So basically, how we define the nodes and arcs and the relationship between them, this defines the structure of the network and the conditional probabilities of the parameters given the structure. Like for example, this one, these are the parameters we have got for this particular node. Okay, we are just a basic description I'm giving it. So the graphical models are frequently used to visualize the generative models. Okay, that means for generative models, if you want to have a visual interpretation, often you'll see that graphical models are being used. For example, in this lecture, we'll be talking about this Bayes network. So the Bayes network can be represented with a graphical model. Okay? So just to have an example over here. Okay. So in this particular example, if I ask you, okay, what is the probability that today is going to rain? What will you say?
0.5.
0.5, right? Sorry, 0.4. No, I mean from this example.
Here 0.4. Oh, it's
0.4,
0.4.
right? Okay. And what's the probability that it's not going to rain? That is not rain.
0.6.
So basically, it's going to be 0.6. Okay. So in this graphical model, okay, what we have, so in this case, we can say there's another random variable, which is the grass, the status of the grass being wet or not. Okay, so this W means basically it's wet. So we have two random variables here. For one is the rain status, another is the grass status, so whether it is wet or not. Okay, so if I write like this W, and since you have an arrow over here, so that means basically the grass being wet or not wet is basically is somehow, we say that it's somehow dependent on this random variable rain. Okay, that means if it rained, okay, what is the probability that the grass will be wet? So they have given this probability that is going to be what? 0.9. Yes. Okay. And if I ask you that if it rained today but the grass is not wet, what's the probability then?
0.1.
It's 0.1, right? Similarly, that it did not rain but the grass was wet, the probability was the probability of wet was 0.2. So if I ask you, okay, the probability of not wet, given that it didn't rain, the probability is going to be 0.8, right? Yes or no? Okay, so if I simply ask you, okay, simply I just want to find the probability of the grass being wet, only this term. So how can you find it? So basically, if you just simply from the rules of probability, we can find the probability of the grass being wet given it rained, the probability of it rain plus the probability of the grass being wet given that it did not rain, and times the probability of that it did not rain. Yes or no? Is it clear?
Yes, sir.
Okay. So do you get this value? What is this value? This is 0.9. So if I just write it at the bottom, this is 0.9. What's the probability of rain? It is 0.4. What's the probability of it? It did not rain, but the grass was wet. What was the probability? Here, right? It's 0.2. And the probability of that it did not rain, what was that? It was 0.6. So whatever the value you have there, that's the probability of that the grass is going to be wet, regardless of whether it rained or not. Okay. Now, if I ask you the other way around, okay, other way around means if I ask you, okay, let's say I want to know, given the grass being wet, what is the probability that it rained today? Can you find it out? It's very easy, right? Because now since we have got all the values in our hand, so according to this base formula, okay, the base formula, I can write that this is going to be the probability of the grass being wet given rain, probability of that rain divided by probability of that grass being wet. Yes or no? So do you have this term? Yes or no? You have it over here, right?
Yes.
Do we have this term? We have it over here.
Yes, sir.
And do we have this one? We got it from here, right?
Yes.
So that means basically what we are, let's say, if I define, okay, this is the class. Okay, this is the class label. That means it's rain, and this is the feature. This is the feature X. So basically what I'm computing the probability of the class given the feature value X. This is actually basically what I'm computing. That means I'm computing the posterior probability. Is this understood? Okay. So this is basically what we're going to do because of classification. We start with that, okay, the feature value is given. Okay, and I want to know that for the kth class, okay, what is the probability? Okay, so if I have multiple classes, let's say class 1, class 2, class 3, and so on. So what I will compute the posterior probability of each of these classes, and then which class will you take the decision in favor? Which one will you take in favor? The class with the maximum posterior probability, right? Yes or no?
Yes, sir.
Okay, so already these things we have talked before actually. Okay, anyway, So in the last class, I've talked a little bit about this base classifier. So we already know that the base classifier will have a strong assumption, okay, that the feature elements, okay, because we represent the feature as a vector x, where we have this element x1, we have this element x2, up to we have n number of elements, okay. But in case of base classifier, to make the calculation simple, what they assume that each of these features x1, x2, xn, they are basically uncorrelated from each other. That means they are independent of each other. Okay, so this basically what makes this classifier very simple. Okay, makes it very simple, and you can work with very large feature set. Okay, you only have to work with this n number of features. Okay, that's very easy actually. And how does it work? So this is a graphical representation that we have seen. Let's say this was the class C, and let's say you have the n number of features. Okay, so what we have, this line represents that given the class C, okay, that means given the class C, the probability of x1, that then we will have this corresponding probability as associated with this one. And again, if you consider the second element, let's say if we consider x2 over there, so now we can say that x2 is only dependent. Okay, only dependent on the class. It has nothing to do with x1 or other feature elements. So we are only considering the probability of x2 given class. Okay, so with this figure, basically we have a graphical representation of this naive base classifier. Okay, so let's move on. So here's the applications of naive Bayesian classifier. Already one of the group they have seen that, okay, how to predict the sentiment from a paragraph or from a tweet or from a post in social media. But the naive Bayesian classifier can be used in some popular application domain. For example, disease classification, if a patient has cancer or not. We can extend it to multi-class classification because we are simply computing the maximum among the probability values. In natural language processing, it's a very common way and very, this popular technique to use this naive Bayesian classifier for text classification, spam filtering. That means in NLP, you will often come across this naive Bayes classifier in the earlier papers. Also, you can build a recommender system. Recommender system means whenever you are browsing to a online bookstore, okay, you will see that they will going to give you some recommendation, what kind of book you might like. Okay, so what they do, they try to combine this naive Bayesian classifier with this scalability filtering. So also in this course, we'll be talking about scalability filtering, so that it can recommend you which type of books or which kind of movies or which kind of music you might be interested in once you browse through the website. Okay, so a lot of applications are there. I just listed a few of them. Okay, and specifically the sentiment analysis, you will see that from a, let's say I have given a post like this, whatever is written over there, I want to know whether this post represents a positive mood or it represents a negative mood, okay, or negative sentiment. Okay, we can do this classification. But the main thing is that what we have to do, we have to extract features. So in case of text classification, what can be the features? Can someone tell me, especially from group 2B?
So it's the words.
Yes, it's the frequency of words, right?
Yep.
Here, what we have used, the feature we have used is basically the frequency of that particular word appearing in that particular sentence. Okay. Anyway, so you will see that more in the lab. So now how it works. So already I talked about this one. So what we do, we compute the posterior probability. Okay, that means we compute the probability of the class given x. So this x means it's a feature vector. So if I extend it, so we have all these feature elements over here. Now we know that from the Bayes theorem, probability theorem, we have this posterior probability split it into this likelihood times prior divided by this evidence, right? And I have mentioned earlier that since in case of two-class classification, what I'll try to do, I try to compute this posterior probability for class 1. I'll compute this posterior probability of class 0. Let's say class 0 means this is a negative class, and 1 means this is a positive class. If I do this, so if I break it down, so basically what I will have on both sides, I will have on this side, I will have this likelihood times the prior. Then I will have on the other side, I will have this likelihood times the prior of class 2, and then we're going to have divided by probability of x. We are going to have probability of x, and since we are now comparing, that is, if the positive class have higher posterior probability than class 2, then we'll take the decision in favor of class 1. And if it is the other way around, that is class 2 has a higher posterior probability than class 1, what we'll do? We'll ascend to class 2, right? Yes or no? So we can see that in case of comparison, as I've said before, we don't have to worry about this constant term that we are dividing, because on both of the sides we are divided by the same term, probability of x. So that's why what we'll do, we'll simply remove this denominator. And if you remove this denominator, you'll see that the terms will no longer appear as probability terms, because they are multiplying two probability terms together. Okay. So I will give you an example later. So that's why you'll see that in most of the cases you'll see that they will simply write the posterior probability equal to the likelihood times prior. Okay. Whenever we are doing this comparison, I will write like this. Okay. Probability of x given class, that means the likelihood, times probability of class, that means that's the prior. And if you combine the two terms together, you can see that basically you're computing the joint probability distribution at the probability of x given class. This is basically what we are computing. The same thing that I've written at the bottom. Okay. So that means the numerator is basically equivalent to this joint probability model, right? Now, how we do this expansion? So as I have said, so we have this joint probability distribution that from where we have started. We have started with probability of class and x, right? And if I extend x, I will have x1, then x2, then up to xn. Okay. So if I bring this notation at the end, this is going to be probability of x1, x2, and xn and class. This is what will happen. So according to this probability rule, we know that if we have probability of A and B, we can write this is probability of A given B into probability of B. This is actually how we can write, yes or no? Right? Or if I say probability of A and B and C, this one I can write as probability of A given B and C into probability of B and C. This is actually what we can do. So since I have x1, x2 up to xn and class, what I will do, I will write it this way. So I will divide it like this. So probability of x1 given. So you see, so this is as if this is A. X1 is only A, and the other terms are B, C, D, and so on. So we can give given the other part for the random variables that we have into the probability of the other part of those random variables. Is this clear? Yes or no?
Yes, sir.
And then we have seen that since x1 has nothing to do with x2, x3 up to xn, but it is dependent on class, right? So that's why this first term I can write as probability of x1 given class. Then the other term is going to be there, that is probability of x2, x3 up to xn given class. Oh, not given class, sorry. And class. So that means this term, probability of x1 given x2 and x3 and xn and class, since we have assumed the features are independent, that's why x1 is no longer dependent on the other features x2 up to xn. So that means in this case, if I say that A is not dependent, okay, it is not dependent on B, then in this case I can write probability of A given C, then probability of B and C. Yes or no?
Yes, sir.
And then the other term you have over here, if you want to expand that one, again I can write probability of B given C into probability of C. I can write like that, right? So that means now if I want to expand the other term over here, how can I expand it? If I want to expand it, I can write like this. Again, similarly, I can write probability of x2 given x3 and x4 up to xn and probability of class. Then probability of the other terms, that means probability of x3, x4 up to xn and class. This is what you can do. And again, if I look at this particular term over here, x2 has nothing to do with x3 up to xn. So this term, basically, I can just write it like this. This is going to be probability of x2 given class. And then you have this other term over there. So in this way, if I keep doing this recursively, that you can see this recursive term over here. If I keep doing this recursively, that means you can see that the feature value xi, the ith feature value, is no longer dependent on any of the successive terms. It is only dependent on the class representation. So that means if we come up from here to there, and if you go on expanding, you'll have something like this, and you will see that this will end up being something like this. That means this will end up being probability of x1 given class, probability of x2 given class, and this way probability of xn given class. And finally, what do we have? Like we have got here, we have the prior probability of the class. And since all these are multiplicative terms, and we have some similarity over here, like they are x1, x2 up to xn, so that's why this whole term can be written as, so you can bring the probability term at the very beginning, probability of the class, that's the prior class, and this is the product of what? The product of the probability of the ith feature element given the class, right? Yes or no? Is it clear?
Sir, I did not get the last part, sir.
Which last part? This one?
Yes, sir. How did we come here?
Oh, this is the this pi symbol means what? This is the product symbol, right?
Yes, sir.
So probability of x1 given class multiplied by probability of x2 given class multiplied by probability of x3 given class. So that means all these things are being multiplied together. That's why we have probability of xi given class. So this means, this part means, if I try that, this part means basically only this part. It is clear.
Yes, sir. It's clear.
Okay. So if you understand this, so basically where have we started with? We have started with probability of the class, or the kth class of course, given x. Okay, that means we have to compute the posterior probability of the kth class, and this one we have converted into, okay, this one we have converted into the likelihood, that means probability of, or we can just simply write the joint probability distribution. Okay, let me write the likelihood first. X given class into probability of class, and then there should be divided by probability of x, right? Yes or no? So if I omit that one, so I can say that okay, posterior probability is going to be proportionate to this term on the right hand side, and this whole thing we have seen that this is basically what we have written as probability of x1 given x2 up to xn, and then class. This is what we had. Okay, and then according to our expansion, we can write this as probability of class, prior class, and then the product of the element wise likelihood. Yes or no? So do you get it here?
Yes, sir.
Okay. Now you can see that all of these things are coming as multiplicative terms. Okay. So what we can do, if we take a log, let's say if I take a log over there, as if basically what we're taking a log over there. If we take the log, what's the benefit of having the log term? What's the benefit? So multiplicative terms will come as additive terms, right? Yes or no? So I mean this will become, if I write at the top, this will become, this say the log of the probability of class plus summation, because this multiplicative term will appear as some additive terms. So it will be log of the element wise likelihood. Is this clear? Yes or no? Okay. So that means what we see that we have this equation. The equation is very simple. Other use the log likelihood. Okay, because what do we have here? Do you have the log likelihood over there? Yes or no? Yes, right? So this is the element-wise likelihood, and you've taken the log, so you have got the log likelihood. Okay. So what we can do, we can either compute in this way, but this one is a little bit, I mean, sensitive, because if one of the terms is 0, what will happen? The whole term will become 0, right? Again, you can see over here, if one of the term is 0, taking the log of 0 is going to be what? It's going to make you an undefined value, right? Yes or no? So there are different ways to take care of that one. So what we can do, we can simply add the epsilon value, this probability value, to take care of that one. Okay? So for the time being, you don't have to worry about that. Okay? So let's assume that okay, this is actually what we're going to use for computing our posterior probability. And the only thing you have to do is that you have to compute this posterior probability for different values of k and assign the sample, that is unknown sample, because you are always computing this probability of ck given x. So you want to know this x should belong, where it should belong to, okay? Where you want to classify it, okay? Where to classify. So this is what you do. What you compute the argument x, okay, for different values of k equal to 1 to up to the number of classes, okay, and then you pick the one with the highest probability, right? Yes or no?
Yes, sir.
So that means, as I've said over here, so what you do, that means your predicted class is going to that particular class k, for which you will get the highest probability. Okay. Now to move on with the simple example. Okay. So let's say you have a lot of records. Okay, you have a lot of records, and from those records, what we're going to do, we're going to compute the frequency table. Okay, frequency table. Let's say that the problem at hand is that whether you want to play golf or not. That means, let's say, depending on the weather condition, you play golf. Okay, let's say for the last, let's say 14 days. Okay, for the last 14 days, we have listed the weather, and we have played either golf or we didn't play golf. Among those records, we have found that among those 14 days, we have 9 days we have played golf. That is, yes, we have played golf, and 5 of the days we did not play golf. So if I ask you, what is the probability that you have played golf? What is the probability?
9 by 14.
It's very simple. So out of 14 days, 9 days you have played. So this is the probability of you are going to play golf. And then the probability of not playing golf is basically 5 by 14, right? Okay. Now the weather condition has been represented by 4 features. Number 1, x1 is the outlook, x2 is the temperature, x3 is the humidity, and x4 is the wind nature. Okay. Okay. That means whether you have, let's say, in case of x4, in some of the records, let's say if you have this table, the table which contains different weather conditions, and then you have taken the decision, okay, whether you have played golf or not. Okay, so some of the records contains yes, some of them contains no, something like this. Okay, so I'm just showing you an example right here. And then here you have these different feature values. Now among those 14 records, you can see this feature outlook. It has 3 states: sunny, and then overcast, and then rainy. Okay, among those 14 days, as you have seen that you have played golf for 9 days. So the days where you have played golf, 2 of the days were sunny, 4 of the days was overcast, and 3 of the days were rainy. On the other hand, 5 of the days you have not played golf, and on those days, even the day was sunny, but you didn't play, right? Whenever there was overcast, of course, you didn't play over there. And then if it was raining, you didn't play. Okay? Do you understand what we have listed over here? We simply have built what we call the frequency table. Okay? The frequency table. And what we do from this frequency table, we are going to convert into probability values. So once we convert into probability value, we basically build the probability table. So the thing is that, given that you have played, okay, what is the probability that you have the weather was sunny? Just a minute, okay, just a minute. Okay, so for the given class, so if I ask like this, the probability of the outlook, so let's write like the outlook was sunny, given the class you have played golf. What is going to be the probability value?
2 divided 9.
2 divided by 9, right? Because given yes means how many days have you played? You have played 9 days, and among those 9 days, how many days was sunny? Only 2 days was sunny, right? Do you understand this one? So similarly, now you can see that once you have built this frequency table, it is very easy to compute the probability value. So that means the probability for given a class yes, that means you have played golf. The weather condition was sunny, it's 2 by 9, or overcast is 4 by 9, or rainy is going to be 3 by 9. And given the class that you didn't play golf, okay, the feature value was sunny, that means the likelihood of being sunny on those days is 3 by 5, 0 by 5, and then you have 2 by 5. Understood? That means basically what you have built 2 probability lists. That is, one is the probability of x1 given the class yes, and the other, so okay, let me write, or you have computed the probability of x1 given no. This is actually what we have listed from here. And group 2B, already in your lab, you have seen that you had to calculate these probability values individually. Yes or no?
Yes, sir.
Okay. Now let's go for the feature temperature. Okay? Temperature is basically, let's say it's represented by x2. Same thing. How many records do we have? We have in total, we have 14 records. That's good. And among these 14 records, you can see the you can build the probability of x2 given yes or given no. And since x2 will have different state, it can be hot, it can be mild, it can be cold. Okay, you can compute the corresponding probability value. That means you can compute this probability table. And the same thing we'll do it again and again for each of the features. Okay. So for 2B, you'll see that once you're working with a sentence, so you have to consider all possible words, right? Yes or no? Because you have considered each individual word as a feature. So if in your dictionary you have 1000 words, so that means your feature vector will contain how many elements?
So 1000 unique words.
1000 unique words. That means your feature element will be 1000, right?
Yes.
And once you have your dictionary, actually, what you have to build? You have to build the probability values for each of the modes. Let's say if we are doing this sentiment analysis, let's say you are in a positive mode, okay, and then let's say you're in a negative mode, okay. So if I have a post, that post will contain a lot of words. If I have a negative mode, that post will contain a lot of words. So what can I do? I can convert it into a feature vector, and that feature vector, and if I have this training data, from that training data, what we have to do? You simply have to compute the probability of that particular word being the class positive class or being the class negative class, right? Anyway, so if I now ask you, do you have all the probability values in your hand? Yes. And does the feature x1 somehow is it dependent on x2 or x3 or x4? Yes or no?
No, sir.
No. Fine. So this is actually what we are going to do. We have assumed each of them being independent, and this is actually how we will try to proceed. Okay. Now we have all the calculation in our hand. Now we'll go towards our inference stage. And in case of inference stage, what we'll do? Okay, we'll do this classification. Okay. To do this classification, if we move next. Okay. Let's say today is a day and the weather status is something like this. The outlook is sunny, temperature is hot, the humidity is normal, and the wind is false. That means we don't have any wind. Now, if you want to decide whether you should, you're going to, if you want to predict whether you are going to play golf or not. So what you will compute? So basically you will compute the probability of, let's say you want to, okay, let's decide it for, yes, I'm going to play golf given the today's, let's say if I write like this, the today's weather. So if this is the case, what should I do then? I have to compute the probability of being sunny given yes, right? Times, if I just don't do this log operation here, then I have to compute the probability of the temperature being hot given the status that I played times the probability of the humidity being normal given I played golf times the probability of the wind being false, given the probability of played, multiplied by the probability of I played, right? Yes or no?
Yes, sir.
Okay. So if this is the case, so if I tell you to find the values, can we do it? So what is the probability of that? That means the probability of the day being sunny and given that you have played. Where is that one? Okay, let's move all of this.
2 by 9.
This is what you have. This is going to be 2 by 9. Okay, so that means you have 2 by 9 multiplied by, okay, the temperature was hot and you have played. Where is that one? This one, right?
Yes.
Now again it is 2 by 9, and then you have the humidity was normal and you have played. Where is that one? Humidity is normal, you have played. This is that one, right? So it is 6 by 9, and then finally the wind was false and you have played. So where is it? The wind was false and you have played. It is what? It is 6 by 9 times finally this prior probability of you have played. What's the prior probability you have played? Sorry, this one, right? Yes or no?
Yes, sir.
Okay. So this is what we have. So it is 9 by 14, and if you calculate, you will see that the value will be something like 0.1. Okay, not 1, 0.0141. This is what we have. On the other way around, if I want to calculate, if I just write over here, if I want to calculate the probability of that, no, I won't play given today's weather condition. If I say like this, so you have to do the same thing, except that given, I mean, it should be probability of sunny given no, right? And what is the probability value? That is, given the class no, the weather was sunny.
3 by 5.
3 by 5, right? So it's going to be 3 by 5 times hot, given that you didn't play. What is that one? 2 by 5, right? It's going to be 2 by 5. And then normal, given that you did not play. Where is that one? This is that one. That given no, you didn't play, but the weather status was, the humidity status was normal. So this is the probability. So basically I have 1 by 5. And then finally, the wind was false, given that you didn't play. Sorry. Where is that one? Is that one, right? So you have 2 by 5. And finally, over here, what we have? We have probability of yes, but for this case, we have to compute the probability of no. And what is the probability of no? 5 by 14, right? Yes or no? So we have 5 by 14. This will be equal to what? 0.00, something like 68. So now, if you want to make the prediction whether that you are going to play or not, what should you do? You take the decision in favor of which class? Yes class or no class?
Yes, class.
Yes class, because the yes class has higher probability than the no class. Correct?
Yes.
Yes,
But the
sir.
thing is that these two probabilities should add up to 1. So do they add up to 1?
No, sir.
So why they don't add up to 1?
So there are other combinations of conditions that we're not considering.
Because you remember that you didn't divide it by the normalization terms, right? You have computed the posterior probability, but you only took the numerator. The numerator was probability of class, the kth class, and x. This is actually what you have computed over there, right? But you didn't consider these normalization terms. You just proceeded from there. That's why if you add them together, they won't exactly add up to 1, because they are not exactly probability terms. Because if they were probability terms, then the probability of yes given today's temperature and the probability of no given today's temperature, they should add up to 1. But in this case, you can see that they don't add up to 1. But still, you can see that this probability is higher than that one. Since we are comparing, that's why we omitted the normalization term probability of x, right? But yet, if I want to convert them to probabilistic term, what can I do? Since I know that these two probabilities should add up to 1, so let's say what I do, I can simply do this normalization. Normalization means this way. So if I want to normalize this one, so just let me write over here. I can say, okay, probability of yes given today's temperature I can divide it by whatever the probability values you have got. Okay, so what the probability values we have got here? So it is 0.0141 plus, and what the probability value we have got for no, that is 0.0068. Okay, so I think this value is going to be something like 0.029209 or maybe something like that. 0209, okay, something like that. So that means if I divide 0.0141 with this value, the value will come up to something like 70. Sorry, the value will come to something like 67. Okay, it will come to something like 0.067. Okay, this is what it will come. And if I want to do the same thing, okay, if I want to do the same thing for, let's say, the no class, okay, if I want to do this normalization, so what do you have to do? The probability of you didn't play today given today's temperature, if I write like this, divided by the normalization term, that is 0.0209. So this is going to be what? 0.0068 divided by 0.0209, and this will come up to something like 0.33. That basically I have simply done normalization, right? Yes or no?
Yes, sir.
And now once you see, once I have done this normalization, then 0.67 and 0.33, both of them, they will add up to 1, right?
Yes, sir.
Okay. So, but still you can see that this probability of playing golf had a higher probability. Even if I have done normalization, still this one is higher, right? That means the relative magnitude is still higher, whichever was higher before. Okay. So that means even without normalization, you can take the decision. Yes or no?
Yes.
Okay. So do you understand now how this Bayesian Bayes classifier is working?
Yes, sir.
So these are basically the pros and cons, that means the advantages and disadvantages of the Bayesian class. Just have a look, okay? So, but the main difficulties with this Bayesian classifier that you can see over here, if you have this zero probability, okay, whenever you do this multiplication, okay, you will be unable to make a prediction. Okay, this is often known as the zero frequency problem. Okay, another main problem is that you assume the features to be independent. Okay, so in the real life, okay, it's almost impossible to get all the features which are completely independent. Okay, this is very difficult, but still, with this basic assumption, you will see that in most of the cases, you'll see that the output will give you, I mean, high result, high accuracy. Is this clear? And of course, you have a lot of benefits, right? First of all, it's very fast, very easy. And if the basically the independence assumption holds, then of course the Bayes classifier will perform the best. Okay, and it is also well suited to numeric values. Okay, in case of numeric values, you simply have to do some normalization with the Gaussian distribution. Okay, this is something I didn't explain here, but you can just keep in mind. So if you are working with numeric values, okay, you can do some normalization with the Gaussian distribution. Okay, just keep this in mind. The other thing that you're going to see in the lab class actually. So now, if I talk purely from the point of two-class classification, so what did I do? I had to compute the probability of class 1 given x, that is the posterior probability. I have to compute the probability of class 2 given x, that means let's say this is the positive class and this is the negative class. This thing like this. Okay, like this is positive, and let's say this is negative. So what we do, so if we have like this, that means the posterior probability of class 1 is greater than the posterior probability of class 2, then this feature x, where will you classify it to?
Class 1.
Class 1. That means you classify the positive class. Now, if I break it down, we know that we can write it like what? This. The likelihood times the prior, and then I will keep this greater than symbol here because I assume that I will classify it to class 1. And then on the right hand side, I will have the likelihood of class 2 times the prior. Okay. And then what I have seen over here. So if I simply take the log likelihood, or okay, forget about the log likelihood. Okay, I do some re-ending term. I bring this term over here and that term over there. If I do like this, if I bring all this likelihood on the left hand side, I have this probability of x1 given class 1, probability of x. So did I write x1? No, I haven't written x1, and the denominator should be x2. Sorry, my mistake. X given class 2 greater than probability of class 2, probability of class 1. This is what we have, right? Yes or no?
Yes.
Okay. Now the thing is that what is the benefit? If I take the log on both sides, what's the benefit? So I have the log of probability of class 1 plus, sorry, it's going to be minus, right? Minus log of probability of x given class 2 greater than, let's keep it like that. Probability of prior of class 2, prior of class 1. Then we know that if we take the log over here, what happens? What happens? So this is a feature vector. So I will have all those terms. So log of, see if I take this summation over here, I equal to 1 to n, the log of xi given class 1. Yes or no? Yes or no?
Yes, sir.
Okay. How about the second term? Minus there, again, the summation will come from the equation from 1 to n and have log of the probabilities of xi given class 2, right? Then the right hand side you have this log of probability of class 2, log of probability of class 1. This is what we have. Now you can see here, one of the terms is going to be log of probability of class 1 given, log of x1 given class 1. On the right hand side, on this side, you'll also have the log of probability of x1 given class 2. So if I bring them together, can I write like this? Log of probability of xi given class 1 divided by probability of xi given class 2. Can I write like this? Yes or no? Where was it? Okay, everything got lost. Okay, I have to write it again. So it was something like this, summation of I equals to 1 to n, and you will have log of the probability of xi given class 1, probability of xi given class 2. Will you have something like this? Yes or no?
Yes, sir.
Okay, so I believe the lab from group 2, you have seen this equation, right? Yes or no?
Yes, sir.
Okay, and you have seen that if the prior probability of class 1 and class 2, they are equal, so what will happen? This term will become 1 and log 1 will become equal to what?
0.
0. So you see that this becomes something like 0. That means basically what you do, you're comparing the log likelihood ratio and then you're comparing against a threshold value that is 0. If the priors are same, remember this is what is important. If the priors are same. But if the priors are not same, then what you have to do? This will become simply log of the prior of class 2 divided by the prior of class 1, right? And if this log likelihood ratio exceeds this threshold value, then we know that we will assign the particular sample to which class? To class 1. Understood?
Yes, sir.
Okay. So that's why you will see in your lab. So if the priors are same, say if the priors are same, priors are equal. So what will happen? This will become 0. And if this will become 0, if the log, so now we call this is the log likelihood. Now we call the log likelihood ratio. So if this value is positive, then basically what's the decision? The decision will come in the favor of the positive class. If the value is negative, the decision will go in the favor of which class? Class 2. That means this is the positive mode. and this is the negative mode. Is this clear? So I believe now group 2 you can relate those values and how you have come up with this comparison, right?
Yes, sir.
Okay. So any questions up to now? No? Okay, good. Okay, so I'm giving you the link to your online attendance. You can fill up the form. Have you got it?
Yes, sir.
Okay. Questions? No question? Okay. So please keep in mind, so next week we're going to have our quiz. Maybe it's going to be on Thursday or Friday. Okay, you decide and let me know on Monday. Okay. The syllabus will be all the topics after the midterm exam that we have covered. Is that good enough? What do you think?
So I think it's a bit large for one piece.
Okay, then let's remove this base classifier, and we only remain with our neural network, the remaining terms of neural network and deep learning. Okay, just let me know on Monday. Is it clear? Okay, thank you. That will do. So we'll meet next week, inshallah. So we'll be starting with decision tree.
Okay, sir. Thank you. Assalamu alaikum.
Okay, thank you. Welcome.
Assalamu alaikum.
Assalamu alaikum.